Hello, everyone. I hope you guys are doing great. In this video, I'm gonna briefly talk about all the necessary concepts you need to complete Lab 5. We are gonna discuss some of the major concepts behind Lab 5, and we are gonna break down some parts of your code so that you can complete the rest of your code to complete Lab 5. And I hope this video gonna help you to understand Lab 5 concepts uh, more. And please don't forget to go through the manuals, the lab manuals and the microcontroller manuals to uh, understand fully how the whole thing is working. So let's start. So in Lab 5, before jumping into the problem, let's think about that. As we already know, we connect a lot of peripheral devices with our microcontroller, and we need some kind of communication to make the whole system correctly functionally. Make the whole make the whole system work functionally correct. And we have two primary methods used for this kind of communication between the microcontroller and the peripheral devices. The first method is, we call it polling, and the second method is interrupts. So polling is a method where our CPU repeatedly checks the status of the peripherals if they need anything, or basically if they need any attention or not. For interrupts method, interrupts are basically signals from peripherals to the CPU, and it indicates that they require some processing. So it is asking you to help on some tasks, and after helping on that peripheral devices, you can get back to your own work. So these two concepts you can easily understand through an analogy. Imagine a library, a large library with numerous sections and a central help desk where librarians assist visitors with finding books and answering queries and providing recommendations. In terms of polling, the polling is basically a routine check. So in the polling part of our analogy, the librarian periodically leaves the help desk to walk through the library sections. As you can see here, we have different sections, and checking if visitors need any help. This routine check is akin to polling, where the librarian, here the librarian acting as a microcontroller, actively seeks out requests to task, seeks out request or task to perform, regardless of whether anyone immediately needs help or not. The pros in that situation is that every section gets regular attention, ensuring that even the shy visitors like me or those who are unsure asking for help directly will receive assistance. The cons are this method might not be the most efficient use of the librarian's time, as they could be checking on sections where no one needs help, while the visitors elsewhere might need immediate assistance but have to wait until the librarian makes their rounds to that section. So now we got how the polling is works. Now let's talk about the interrupt. So you can think about interrupts as a the call button, the emergency button, like 911. Now imagine each section has a call button that visitors can press when they need assistance. This button signal to the librarian at the help desk, similar to an interrupt signal to a microcontroller, that someone needs help, right? The librarian immediately pauses their current task to attend to the caller's needs. So here, the pros is this method is highly efficient, right? As the librarians, assistance is provided exactly when and where it is needed, without wasting any time or unnecessary checks. The cons are, if many visitors, for example, they're pressing their call buttons simultaneously, the librarian might be overwhelmed and needing to prioritize which request to respond to first. This can lead to delays in assistance, similar to a microcontroller if they are handling multiple interrupts. So now we know during the communication how these two primary method works, that is polling and interrupts. So in SiFive, we have like we have some harder architecture to working with the interrupts. So based on the source of the interrupts, there are two main forms of interrupts in the SiFive processor. And we call them local and global interrupts. So let's think about this way. The availability of different techniques for interrupt is processor specific, right? For different boards, there are different techniques based on the source of the interrupts, from where the interrupt is generating. We can categorize the interrupts in two categories, that is local and the global interrupts. The local interrupts are generated based on some activity internal to the processor. They can be generated using software running in the processor, or a timer that is counting towards a certain number. So the local interrupts is solely the software based. I mean, the CPU is maybe, checking something or counting something for a specific time. For the global, the interrupt, or we can also call them the external interrupts. The external interrupts are interrupts from the external devices, as the name suggests, such as GPIO, UART, or I2C, etc. To handle the local interrupts, the SiFive processor has a module called cleaned. In the previous labs, if you observe the code, the libraries, you should observe we already used this cleaned hardware to calculate the delay. And yep, you are right. I mean, cleaned is a local interrupt hardware that SiFive processor has. And the full form is core local interrupts. In short form, we call them cleaned. And this client is directly connected to our microcontroller, and it has some other a part like machine timer interrupt and machine software interrupt that is used to create a different kind of interrupts as you need. So we'll talk about more for the next labs. Now, for this lab, we have to understand a very important register. And this register, is managed by Clint. To handle the global interrupts, I mean, we are talking about the local interrupts. To handle the global interrupts, we have other module or hardware. We call them PLIC, but the global interrupts are out of the scope for our lab. So we'll only stick to our local interrupt that is cleaned. And inside this local interrupt cleaned, we have the M time register. And if you can observe, our M time register is basically the timer register. So as you already having an intuition that we can calculate time from that register. And if you see, usually we are comfortable to see 4-byte width of register, but this register is not 4-byte. This register is 8-byte. That means this is 64-bit register. And the reason behind this huge number, because as you can see, this M time is calculating time. So we might need to run our hardware maybe like 2 or 3 years, and as it is continuously running or counting, so we might overflow the number of 32 bits. So that's why this M time register is more than 32 bits, and here this is 64 bits, and we can there is a calculation I can tell you directly. I mean, to fill the 64-bit number in a certain frequency, we might need for example 300 years. So we don't need that much amount of time. So yeah, we are perfectly fine with 64-bit numbers, but may we not even utilize all of the bits. So yeah, I mean, our Splint core local interrupt is responsible for managing local interrupts, including the software interrupts and the timer interrupts. And it provides us this timer register for real-time clock and other timer functionalities. And our M time register hold the count of clock cycle passed by the CPU. So when we turn on our CPU, here CPU is exactly as we are describing the microcontroller. So whenever we turned on our microcontroller or CPU, it start counting the clock cycle passed by the CPU. So you know the clock is kind of the brain of a CPU, because every operation is happening based on the clock frequency, right? For example, I mean, why I told you, I mean, the clock is the brain of the CPU. For example, if you think about yourself, you are, for example, if you are watching a TV and suddenly you think you need to change the channel, and to change the channel, so your brain got a signal from inside of you to, telling you to change the channel of your TV. So this clock is basically, I mean, is a pulse continuously from 0 to 1, 0 to 1. And each clock pulse is trying to, tell the whole CPU what things to do next. So that's why, I mean, the clock cycles are kind of heart of the CPU, or brain, whatever you can say. And so when we turned on our CPU, the clock cycle is continuously running from 0 to 1, 0 to 1, 0 to 1, 0 to 1, and so on. And we have a specific frequency for this CPU, and we have different clock source to generate these clock cycles. So we have the real-time clock, and it is a real-time clock where I mean, it is located in the always-on domain, and the frequency is 32.768 kilohertz, or 32,768 hertz. So what does it mean by the frequency of that clock? So by means, I mean the hertz, when we say our clock frequency is 32,768 hertz, that means we have total, 32,768 clock edges for one second. So basically, the hertz is telling us total cycles per second. And we have, I mean, to pass 1 second in our microcontroller, we need to go through total 32,768 clock cycles. In the next slide, we're gonna go through in more details of this frequency and how we can calculate the time from this frequency. And yeah, I mean, definitely, I mean, if we know the frequency of clock, it is straightforward to find out the time elapsed. So yeah, let's start the most interesting part. Let's go through our codes. So as I already told you, like all the previous labs except lab 1, we use this function get cycles, right? And this is an inline function, and it is returning some value that has total 64 bits. As you can see, the return type is unsigned integer 64 bit. And these get cycles, as the name suggests, there is no argument for this function. So basically it is collecting total cycles from a register. And what's the register? Yeah, the register is cleaned underscore m time. And this cleaned underscore m time is nothing but this m time register. And we know our m time register is 64 bit. That's why we're using an int 64. We have the base address of cleaned, and we are simply adding the register offset and returning the value. And as I already told you, we are using here the real-time clock. I mean, we are getting the cycles from this real-time clock. So this 32.768 kilohertz means we have to pass 1 second in your microcontroller. We have to go through this 32,767 clock edges. So if you start with 0, yeah, it's the 32,767. And each clock period, so we call them clock period from one clock edges to another clock edge. And we can calculate the clock period that is basically 30.518 microsecond here. As we know, this whole 32,768 cycles is basically 1 second. And we know 1 second is 1000 millisecond, and 1 millisecond is basically 0.001 second. And our clock frequency is 32,768 cycles per second. So this clock period, is I believe very helpful to you to understand how we calculate the cycles and how many cycles we need to count just 1 second. Now, to calculate the clock period, it's just basically 1 by the frequency. So this 30.518 is just 1 divided by 32,768. And if we want to validate our information, so we have total, each clock period is 30 microsecond, not millisecond, I'm sorry. And we have total 32,768 cycles. So if we multiply the microsecond with this number, we'll get 1 second. Now, if you understand how we are converting this frequency to second, and we are calculating the clock period from our frequency, now it's very easy for you to calculate the delay. For example, when we turned on some LEDs, we use delay, for example, 0.5 second or 1 second or 500 millisecond. So we use this function delay to to use that time for CPU to do nothing. So as we already know, interrupt is the name, as the name suggests, interrupting means like holding back. It's asking the CPU, please, wherever you are, whatever you are doing, please stop and do this kind of IO operation. So here the delay is basically the IO operation, the interrupt. After you are done with the IO operation here, for example, if we set the delay 1 second, after 1 second, you can go back to your code and resume wherever you are. So that's how the delay is, right? So as you say, we calculate the delay by using this get cycles function. So if we want to set the delay, for example, let's say 1000 millisecond, that is 1 second. So this function just take the number as an integer. So if we want to use 1000 millisecond of delay in our code, we just pass the number 1000, and what you will do, we will do this calculation. So first we try to collect the cycles, because as we know, I mean, this M-time resistor is from the very beginning, it is continuously counting the cycles, and we will collect the current cycles, and uh, we'll add based on our millisecond, we will add that by multiplying with a factor. So this factor is basically telling you like how many millisecond you want to add with your get cycles. So if it is 1000, for example, for millisecond 1000, this equation would give you only value 1000, and that means yes, we can have the delay of 1000 millisecond, right? So the dividing this clock cycle with 1000 is basically, that means we are using this delay function as a millisecond format, right? And the key point here is this get cycles updates inside of the hardware periodically, because this get cycles is using this M-time resistor, and we declared it also as a volatile, which means the computer know the value of this memory address can change abruptly. And I hope now it is clear how we are calculating the delay. So please go through these equations. It's very simple and easy equations. Now we have another function that is delay underscore usec. So the previous delay function we used, it was for millisecond, as I already told you, because we are dividing the number using 1000. Now we are dividing the number with not just 1000. It's more than 1000, because now we are calculating the delay, or we are trying to use the delay as a microsecond. That's why you are using U here. So why we are using microsecond delay here, we'll talk about that in the next slide. But just this function is exactly as the delay function, but instead of the millisecond delay, we are having microsecond delay. That means we are basically controlling our delay more smaller in a smaller time manner. So for example, millisecond is you know, I mean, 1 millisecond is basically 0.001 second, but we know 1 microsecond is very less compared to the millisecond, obviously, than the second. So yeah, I mean, this delay function is nothing but calculating the delay in microsecond, because this lab we are gonna use a motor. The motor we call servo motor, and this servo motor can you know, operate on microsecond. So we'll see in the next slide. But yeah, I mean, this function is nothing but we want to calculate the delay in microsecond, not the millisecond. Now, in lab 5, we have our servo motor, and we are in this lab, we are gonna, you know, rotate our fan of the servo motor and with the help of our microcontroller. So to do that, we will provide you a servo motor, and this servo motor has, you can see it. This is, if you can, you can say it is a fan of this servo motor, which we are trying to rotate, and this servo motor has only 3 pins. The first pin is we are calling the PWM. The PWM means Pulse-Width Modulation. So this servo motor operates on different pulses. So what does a pulse mean? So when we have a clock period, so here you can see we have a clock period of 20 millisecond, and each on portion, I mean the portion where we have the highest values. For example, if our clock period for our clock period, if the lowest value is 0 and the highest value is 5 volt, so the on time of this clock period is basically we are calling pulse, and based on this pulse's width, we can rotate our motor's fan. And yeah, I mean the way the servo motor works with this PWM, the pulse width modulation. The more shrink we these pulses, or the more we expand this pulse, we can rotate our fan of this motor. And the other two pins are just VCC and the ground. It's pretty straightforward. The red wire of this motor is will go into the VCC, that is 5 volt, and the brown wire of this motor will go to the ground connection. So usually, I mean, in the previous slide, we can see here the pulses are equal, right? I mean, for this clock period, we have 50% time it is on and 50% time it is off. So the duty cycle here, the duty cycle term is came from the time it is spent for total amount of time it was on. Uh, uh, so the duty cycle is basically the on time of a clock period. So if let's say here the duty cycle is half, because half of the time it was turned on and half of the time it was turned off. Now the duty cycle or the pulse width can be more than 50%. So here, for example, this 20 millisecond of clock period, if we divide this clock period 20 times, so each times, let's say if this clock period turned on only for 1 millisecond, then the duty cycle is 1 by 20 millisecond. It's very straightforward, right? So yeah, I mean, it's 1 by 20 as straightforward as it is. Now, for our servo motor, our servo motor only works, operates between 1 to 2 millisecond. So to work with our servo motor, we can't use 50% duty cycle. We have to use this 10 to 20% of duty cycle. I mean, we have to create a clock period where only 10% to 20% of time it will be actively on, and the rest of the time it will be off. That means 0. And if we further break down the pulse width, our servo motor, if you think about the operation, it can operate for 0 degree. It will start from 544 microsecond, that is eventually 0.544 millisecond, to 2400 microsecond, that is 2.4 millisecond. So our servo motor operates between these 2 millisecond. So yeah, if we want to rotate our fan from 0 degree to 180 degree, we have to set our pulse width according to between these values. So if we set our pulse width value to 2.4 millisecond, if the duty cycle is 2.4 millisecond, basically 2.4 divided by 20 millisecond, if there's a duty cycle, or basically the pulse, if the pulse width is 2.4 millisecond, our motor will rotate from 0 degree to 180 degree. And our clock period for this servo motor is just 20 millisecond, that is 50 hertz. Now let's observe how we can use different values, like different duty cycle values to, rotate our motor. For example, this is our initial position of our motor. Now the motor's fan position is in 0 degree, and we can rotate it like 90 degree, 180 degree, or we can rotate it in 30, 30-degree interval. We can also rotate it in a 30-degree interval. So the code we gave you in this lab, if you see, this is our main function, and you have to complete this servo function. So inside of our main function, we are trying to rotate the fan in a 30-degree of interval, because as you can see, we start the position from 0, and we went all the way to 180 degree, and the interval is plus 30. Now, to rotate it in a 30-degree of interval, we know when we are in 0 degree, we have to set our pulse width 544 microsecond, and we know we have highest 180 degrees, that is 2400 microsecond. See, if we collect the difference of these two number and divide it, if we are, as we are rotating it in a 30-degree of interval, so we have total 1 2 3 1 2 3 4 5 6, we have total 6 interval, and we can divide the difference by 6, and we can get the value that needs to set to rotate it in different intervals, right? So for example, if we get the difference around 2000, let's say, and the difference between this is, let's say, 1900, and if we divide it by 6, so we have total 300 microsecond for each, for each 30-degree angle, we have 300 microsecond. So as you can see, these values is, we are rotating the fan from 0 to 30 degree, 60 degree, then 90, then 120, 150, and at the end, 180. So as you see at the very beginning, we had the duty cycle of 544 microsecond. Now we added 300 microsecond with our existing pulse width, and now the motor shifted to 30-degree angle. And if we add another 300 microsecond to our pulse width, the motor will go from 30 degree to 60 degree, and so on. So as you see, the pulse width increases, the rotation of the motor is also changing according to the pulse width. So I hope this picture was very helpful to illustrate you how we can control the motor rotation of our servo motor. And in a high level, what you have to do in that function, you have to first calculate the on cycle. Like every time you have to calculate this cycle, like the value you need to add to the existing cycle, and then you have to set the GPIO output well, because we are connecting our servo motor through a GPIO pin, and we have to pass this clock period to that value. We have to pass this clock period value to that GPIO pin, so that the motor can get this pulse width. And then we can use some delay. So as this amount of time was turned on, for example, 544 microsecond was turned on, and the rest of the time for our GPIO pin, we have to set the value 0, right? So for this amount of time, we have to set it 0. I mean, we have to pass 0 voltage on that GPIO pin. And then, yeah, I mean, as you can see here, after calculating the delay, we are making off. We are basically turning off this output value. I mean, we are giving the off value to this register output value. So it's getting the amount of it is getting the off value of this output value register after this amount of delay. And yes, we again use the delay usage. So after turning off, we need to know how much of time here we want to turn it off. So yeah, we again use the delay usage with the off cycle value. So this is very straightforward. Just go through the code, and if you know how to calculate, as you can see already from the picture, you know how to calculate these values. It's pretty straightforward, and in the code you have already the initialized values. As you can see here, the initial values are already given to you, like the maximum pulse we can give to our servo motor, that is 2400 microsecond, and the minimum is 544, and we have the period of 20,000. So this 20,000 period we have to turn on, for example, to rotate the motor fan in 180 degrees. We have to turn on this amount of microsecond, and the rest of the time we have to we have to turn we want our clock period to turn off. So this pin, GPIO pin, is basically for certain amount of time it is getting 1, and for certain amount of time it is getting 0, and eventually this construct a clock period that is that can be readable by the servo motor, and it can rotate the fan based on that way. So yeah, that's all for this lab 5. I hope it was very helpful for you to understand the concept and how you can rotate the fan on your servo motor. Best of luck. Thank you.